Okay, welcome to WASA Distance Education. This is MBF3C, uh, College Prep, Grade 11 Math. I'm Pete, and I'm your teacher. Now, an important announcement about this class and tomorrow's class. They're both pre-recorded, so don't call in. I'm actually traveling on Tuesday and Wednesday, so um, we'll still do the classes, but obviously we don't have any kind of interaction. If you have any questions, you can always send me a Facebook message because I'll check my Facebook. You can send me an email, and or you can just wait until I'm back in the studio on Thursday. Okay, so I will be back, and the class will be live Thursday. So we'll take care of any questions that come up then. Okay. Likewise, if there's anything that's left over from our Monday class, because I don't quite know, so we'll pick that back up on Thursday as well. So anyway, this is week 8 of our 9-week course. So we're doing pretty well here, and today is lesson 19 out of 20. Now, up until now in Unit 4, we've been looking at data management. So the first 3 lessons were really about collecting data and analyzing it. We're going to kind of turn our attention to a slightly different topic for these last 2 lessons, and it's actually an important topic, and very often you can take a whole class on this. It's called probability. So let's take a look in our units. That's going to be on page 21 of Unit 4. And okay, pretty close here. All right, there we go. So it's called, starts with theoretical probability. And we're going to start by just talking about some of the terminology that we use. But just before I get started with that, we're probably all familiar in some way with probability. We think of it as being something for like card games, right, or lotteries or something like that. But in fact, it shows up in a surprising number of workplaces, including engineering, manufacturing, insurance, and finance. All of these uh, uh, places, all these careers have some sort of probability that they use. They collect statistics and they calculate probabilities. Okay, so a good example might be in engineering where you have a part that's critical. Maybe a part in a computer, a part in an airplane, and if it fails, it can cause all sorts of problems, right? So you look at the probability that it's going to fail, and if it's too high, you might do something like you choose a better part, or maybe you'll put a backup in place and spend all that money on something that has a high probability of failure. So yeah, it's used quite a bit. So let's take a look at some of the terminology that we use. So this is on page 19 of your unit 4. Just about done, hey? Just now, in case you're wondering what we're going to do next week, since we're going to run out of course material, what's going to happen starting probably on Thursday is we're going to start the review. Week 9 is actually a short week, and I believe we have, I hope I'm correct, we have Monday off. So we really only have 3 classes next week anyway. Okay, so that'll actually give us a perfect amount of time to just go through the course, do a thorough review, and then you'll be all ready for that final exam. Okay, so that's what's happening next week. So for the probability, we have a few things that we have to kind of know. And as usual in math, we're using the way we use language is maybe a little different than what you're used to. So trials, when we talk about trials, that's the number of times an action is repeated to complete an experiment. So let's say that you're going to flip a coin. Okay, you flipped a coin before, it can be heads or tails, right? So the number of times you flip that coin is the actual number of trials, right? If you flip it 10 times, you did 10 trials. Okay, if you throw a dice, a pair of dice, or one of them, which is called a die, single dice, um, that would also be like one trial if you cast some dice. Okay, so that's what we're talking about with trials. Okay, so and very often it's something like we'll draw cards. We'll draw 5 cards. That's like 5 trials. Sample space. So the sample space is the collection of all possible outcomes of an experiment. And a good example for sample space, if you think of flipping a coin, there are actually 2 possibilities, right? A head or a tail. That's probably the worst H and T I've ever drawn. So let's see if I can get this. Um, that's a H and that's a T, right? So the outcome then, when you're casting a coin, a single coin, you're flipping a coin, the outcome is just a head or a tail. That's the sample space, not the outcome, sorry, the sample space. Okay, if you throw a dice, a single dice, which is called a die, D-I-E, it's got a strange name. That's just a single standard, because dice is actually a plural word. So if you have 2 of them, it's dice. But if you have one of them, it's a, there you go. So if you have 2 of them, whoop, there you go, or more, it's dice, plural. Single one's a die. Most people aren't going to say anything if you say dice when you mean one of them. The problem is that if someone says die, your math teacher in college or something, you won't know what they're saying. So that's why I brought that up. So in the case of throwing a single dice or a die, the sample space could be there's 6 faces on it, right? And with 6 different sets of numbers. So the sample space could be 1, 2, 3, 4, 5, or 6, right? That's the entire sample space for throwing a die, correct? Now, here's something interesting. What is the sample space for throwing 2 dice? Or dice, pair of dice. What is the sample space? What's the smallest number we could have? A 1 and a 1, isn't it? So the sample, the low end of the sample space is 2, right? We could have 2, 3, 4, 5, 6, 7, 8, 9, 10. What's the biggest that we could have? A pair of 6s, right? A pair of 6s. So that could be 12. So that's our sample space for a pair of dice. So this is really the kind of the heart of studying probability, is trying to figure out what the sample space is. And then this next one is the outcome. The outcome is specific and possible result from a trial of the experiment. Okay, so if I am throwing dice, I could ask myself, if I'm throwing one die here, I could ask myself, what is the probability of me getting a 1? Okay. And, well, there's only one face, and our sample space is uh, is 1 to 6, right? But there's only one number 1 on it, so the probability then is there's one face out of 6, or 1 out of 6, right? That's the outcome. Okay, so the probability of getting 1. Now you could say, well, how about what's the outcome if I have that I'll get an even number? Okay, well then you have to look at the sample space and find out how many times that um, number appears in the total possible outcomes. So if I look at a single die, there's 3 even numbers, 2, 4, and 6, out of a total of 6. So the probability that I'll get an even number is the total number of um, possible outcomes for that thing that we're looking for, or target, versus or divided by the total possible outcomes. Okay, so that in a nutshell is calculating the probability. Okay, so that's the outcome. And then the advantage is the probability of a certain outcome. So and actually, I'm getting just a little bit ahead of it here, but that's really what we're looking at there. Okay, and then theoretical possibility, that is when all of the outcomes of an experiment that correspond to an event are equally likely. Okay, so you know, if you're throwing dice, chances are that they're fair dice. But if they're really cheaply made dice, maybe the dice isn't perfectly square. And so if you threw it a lot of times, the theoretical probability would not match the actual probability, right? Maybe the one face is a little heavier than the six face, something like that. Okay. So, but we normally, when we're calculating probabilities, theoretical probabilities, we just assume that they match the reality. Okay. So, so when we're looking at theoretical probabilities, we use a capital P, and then we say A. A is actually, we just use that as a placeholder for um, the event that I'm talking about or that I'm looking at. So for example, if I'm flipping a coin, the probability of getting a heads, I'll put an H there. Well, how many heads are there on a coin when you flip a coin? There's a head and a tail, right? There's only one head, right? But yet the coin has two sides. So the probability of flipping a head on any given trial is 1 over 2 or 0.5, sometimes expressed as a decimal, and then if we multiply that by 100, that would be a percent, right? 50%. So that's really the kind of the fundamental calculation you're going to be making when you look at these uh, probability. Okay, the number of outcomes that make up that event. So in the case of the even numbers, this is how we got this top number here. There's 3 even numbers on a single die, and then divided by the total number of possible outcomes. So in that case, it's 6, right? There's 6 faces. Now things get more complicated when I ask the question, um, you know, for more complicated situations like 2 dice or a deck of cards or 2 decks of cards, then these do become quite complicated, and that's really why we spend our time trying to figure these out. It's very informative to go through some of these. And we have a few tools that we use to help us understand the probability situation. Okay. So example 1 here, it says list all the possible outcomes if a coin is flipped 3 times, then state what the probability of flipping heads uh, on the coin twice. State the probability, not what the, to state the probability of flipping heads on the coin twice. Okay, so there's 2 parts of this. Okay. So when we're making a diagram, there's a couple ways to do it. We're making a table or listing all the possible outcomes. It's easy. You just kind of pick one kind of possible outcome, all heads. Okay, that would be if we're flipping a coin 3 times in a row. This is our first flip. This is our second flip. This is our third flip. So the first one will be heads. The second one will be heads. The third one will be heads. Now you could say, well, that's a very low probability event. Yeah, it is actually. If you look at the a number of possible outcomes, there's 8 of them. That only happens 1 time out of the 8 trials. Okay, 1 over 8 is the probability of getting 3 heads in a row. It's not really tiny, right? You have a it's a lot higher probability than getting the lottery or even getting 1 number on the lottery. Okay, so it's an interesting to be able to see that. Okay, so once you figured out, okay, I'm going to do heads, 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 or you could start with tails, 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 tails. That's the easiest way to do it. And then you just vary the last, right? So it's heads, heads, tails. That's another possibility. And then we're going to go heads, tails, heads, heads, tails, tails, right? And so we're just going to cycle through all of the different possibilities. And then the last one will usually be the opposite of what we started with. So in this case, it's tails, it's 3 tails in a row. So the first question then they ask us, those are all the possible outcomes. So there's 8 possible outcomes. But we want to know, what is the probability of getting 2 heads in a row? So now that we have our table, is it, wait, I just want to make sure whether it's 2 heads or 2 heads in a row. Flipping heads on the coin twice out of the 3. Okay, so let's go check all the ones that have at least 2 heads in there. 2 heads. Now this third one, they're not in a row, but it didn't say in a row. It just said 2 heads. Okay, So for 5, there's 2 heads, and that's it. So there's 4 possible heads. Now I see that they are interpreting it. I can see here that they're interpreting as 2 consecutive heads. Let's have a look at what they said. The probability of flipping heads on the coin twice. Well, in order to match the assumption that they made um, in a row, gee, okay, because otherwise, I think my interpretation of it just being 2 heads, period, would hold. But they're saying in a row, so I have to eliminate the one that where it's not consecutive. So now we have 3 possible heads out of a total of 8. Okay, or 3 possible successful outcomes, right? This is what we're looking for. The outcome, we're looking for the 2 head outcomes. The 2 heads in a row outcome. To make it clear. Okay. Now, the way that they show this here in a table, oh, by the way, just to kind of, so probability of 2 heads in a row is the number of possible 2 head cases, which is 3 of them, divided by the total number of, just the total number of events, of, the samples, the sample space, right? Total number in the sample space, which is 8. Okay, I don't know, this notation is a little different than, I just put the number. I wouldn't put anything in brackets like that. Okay, so it's 3 over 8, which gives us 0.375 or 37.5%, which is surprisingly high. It's not 50-50, it's not 50%, whatever you would say. It's a little lower than that, but still, again, you have a better chance of getting 2 heads in a row, flipping a coin 3 times, doing that 8 times, than you would have, even getting one number on the lottery, I think, 649. You could actually work that out. Now, the way they've shown this table, they just kind of wrote it down and just kind of permuted through the different possibilities, just changed the last letter before it. Another way of doing it is to use a diagram, a tree diagram, and it can be either a vertical tree diagram or the kind which I prefer, just because it's easier when you're doing it on paper, is a as you call it, a vertical? No, you call it a down the page diagram. So what they're saying is that the first coin could be heads or tails, right? So it could be heads or tails. And then each one of these could be heads or tails. You see? So you're going down the page like that. And then finally, this is the first toss. This is the second toss. And then each one of those could be heads or tails. Heads or tails. And you'll actually see that for a lot of the questions we have in this unit, that making one of these tree diagrams, probability diagrams, is actually easier than making a table. Okay. And that's actually the way I like to do it. Not quite so messy though. I don't know what's. I just ran out of room there. Let's see if I can improve this. Whoa. Okay. Well, that didn't improve it at all. All right. Every once in a while. Lock. There you go. This software doesn't let you lock every page in advance. That would be very helpful if you did that. Okay. Let's see if I can make this happen though. Without. All right. Well, not so bad. I think I'm going to take. All right, one more try here. There we go. Group, group, and okay. Now it should work. Now it should. Look at that. I think I got it. Got my little diagram here. Okay, so that's maybe a little better. I got really messy on this last little bit here, the last trial. But there you go. So there's your trial number 1, your number 2, and your number 3. Okay, and these are coin flips, and you put down the probability of each one. All right, well let's take a look at another example. Yeah, you see here, what? Okay, this doesn't. Okay, now I'm confused because they're showing us non-consecutive heads. Oh, only two heads. Only two heads? Wow. Okay, this is pretty ambiguous. Flipping only. Okay. Yeah. Not in a row, so it was just only two heads. Ah. Um, yeah, so needless to say, that question's a little dodgy. I'm going to improve that for the next time. But you can see that sometimes being how they state a probability event, um, it really has to be clear. Now, as far as the key questions go, most of them I think are pretty clear. But if one of them isn't clear, and you're not real sure, just write your assumptions down at the beginning and it'll be fine, right? Because really what we're trying to do is see that you know how to do this, not necessarily that you can somehow decode a kind of a poorly worded question, okay? So this is where things get interesting. What is the probability of picking a red card out of a standard deck of cards? Oh boy. So they assume that you're a real pro on card playing and that you know all about cards. Mathematicians actually do tend to know quite a bit about cards because all of our sample questions are about decks of cards. So here we go. So if you'll think about a standard deck of cards, there's 52 cards. Okay, there's 4 suits. Okay, and there's 2 colors. Okay, so with 4 suits, it means that there's 13 cards in each suit. Right? Oops, suit. I don't know. There's 13 cards in each suit. So what is it? It's you got the ace, the 2, all the way up to 10. So that's 10 right there. And then there's the jack, the queen, and the king. So that's 13. Okay. So if we think about just the red cards, then there's 2 batches of red cards. There's the hearts, and then there's the diamonds. Okay. There's 13 hearts and 13 diamonds for a total of 26 red cards. We could ask the same question about black cards and it would give us the same answer. So the probability of picking a red card from a standard deck of cards, assuming of course everything's nicely shuffled and that there's no cards missing, no extra cards. So it's the total number of red cards in a deck, which we worked out to be 26, divided by 52, which is the total number of cards in a deck, the sample space, right? And that's 1 over 2, 50%. So there you go. If you want to amaze people, you're playing some cards, maybe you're waiting for someone to show up. You just do some probability trials about picking a red card. And you'll see that the first couple, maybe you won't have 50%, but if you do enough of them, you do 5 or 10 of them, it'll start to approach 50%. Okay. All right. So let's take a look at the support questions then. Really, this is, the way to get to understand this is just to do some questions. There's not really much else to this theoretical probability. Okay. And then we have to work through some of the terminology that may or may not be familiar. So let's take a look at the support questions on page 22. And I'm going to make a new page here, but you can keep watching page 22. So this is support question 1. That's on page 22. All right, so the first one is, suppose 2 consecutive coin tosses occur. What is the probability of at least 1 tails appearing as an outcome? The probability of at least 1 tail. So let's make our first trial. So that's going to be heads. That's going to be tails. And then the second toss, going to be heads, going to be tails, and there it's going to be heads, it's going to be tails. Now, what they're asking us to calculate the probability of that at least 1 tail occurs as an outcome. Now, when we do our tree diagram this way, we have to understand that this is 1 possible case. This is another possible case. This is a possible case. And that's a possible case. So in a way, maybe I did a little disservice by putting it that way. But you know what? We can write it down. It's going to be HH. It's going to be HT. It's going to be TH. And it's going to be TT. Okay, so if you just, all I did was I went the first one, the second one, the third one, the fourth one. Okay, 1, 2, 3, 4. So the question is, there probably at least one tails. Okay, so the probability of one tail, well, how many possible outcomes are there? There's 4 possible outcomes. And how many of them have at least one tail? Well, that one doesn't, but that one does, that one does, and that one does. Okay. Or 75% if you wanted to write it in percent. There you go. So that's what they decided, or that's what we find for that first question. Okay. So we worked out the total the total sample space, okay, which has 4 items in it. And then we worked out the number of trials that result in an outcome or an event that we're interested in, which happens to be 3 in this case. Okay. All right, well, let's, I'm just going to extend this page here. So let's take a look at the next one. So question 2. It says using a standard deck of cards. Okay, standard deck of cards, it tells us it's 52 cards. You remember what the standard deck of cards is? You'll get to know it pretty well by the time you're done this. Right, 52 cards, 13 by 4 suits. Okay, I think we got that. Consider the following possibilities. Okay, this is great. So A, we want the probability of picking a 5, a 6, or a 7. Okay, so the probability of picking a 5, a 6, or a 7 is equal to the number of possible outcomes that make up that event divided by the total number of events. So we're just going to pick one card, so our sample space is 50 out of 52 cards. Well, how many 5s are in this deck? Okay. Well, there's 4 suits, and each of them has a 5, right? So there's going to be 4 5s, right? There's going to be 4 6s, right? And there's going to be 4 7s. Okay, so any one of those will satisfy the probability we're looking for. Probability of a 5, a 6, or a 7. Okay. So let's just work out what that's going to be. That's going to be 12 out of 52. And we can actually reduce that to, let's see, if we divide that by 4, so that's going to be 3 out of 13. So 3 out of 13, I don't know. That's the probability. Doesn't really strike me. It's a little under 10%, isn't it? 3 divided by 13. Well, let's see. Oh, not under 10%. 3 under. Well, anyway, so let's just round it off. So it's 0.23 or 23%. Okay, that's not so bad. Okay, so just under 1/4% of the time, not 10%, 1/4% of the time, you're going to pick the 5, 6, 7. Does that make sense? Okay. Now we can double check our answers. This is lesson 19. So yeah, so they got 23% there as well. Okay. All right, so was that A? Okay. So let's take a look at B, and again, we're going to have to really have a look at what the structure of a deck of cards is to be able to answer some of these. If you don't have one, maybe you could borrow one or something. What is the probability of picking a diamond or a face card? Whoa! So it's the probability of a diamond or a face card. Okay, that was supposed to be a diamond. That's not a really good looking diamond. Okay, so one of them or the other. Okay, well, I think we're pretty set that there's 52. Unless they're telling us that it's out of a subset of the deck of cards, we know that the sample space is going to be 52. Well, how many diamonds are there in the deck? Hmm. Okay. This is kind of interesting. Okay. So now we don't want to double count things because there are some face cards that are diamonds, right? So let's just talk about the diamonds that go from ace to 10. Okay, so that's going to be 10. Now, how many face cards are there altogether, which will include the diamond face cards, right? Well, there's going to be three for each of the four suits, right? It's going to be 12, right? There's three. There's the Jack, the Queen, and the King, and it's for all four suits. So altogether then, the diamonds are 10, right? There are 10 possibilities to pick diamond non-face cards and 12 possibilities to pick diamond, or sorry, face cards. So it's going to be 10 plus 12, and I'm just going to skip a little bit down here, and so I got that's 22 out of 52. Mm-hmm. And And so it's going to be 11 out of 26. Okay, 13 plus 9. They got a 21. Okay. Oh, wait. Uh, 22. Oh, yeah. Okay. Well, I don't know, they did it a little differently than I did. So 11 divided by 26. Divided by 26 gives us times 100. Gives us about 42. It's approximately 42%, a little more than 42%. Okay, so not so bad. It's the sort of thing that you would be kind of a fun thing to try and figure out what that would be and then test it. You're playing some cards, as I say, only if you're waiting for someone or if someone leaves and you don't have enough for the game. Now, what's the other one here? What is the probability of picking an even valued, whoa, an even valued non-face card? Okay, they're really testing us here. I'm going to change colors. Um, so an even non-face card. Okay, so um, in a given set of, okay, non-face cards goes from ace to 10, right? But the even ones, there's 2, 4, 6, 8, and 10. Is that correct? And now, and then there's one of those for each of the four suits. So the total number then is going to be 5 cards in each suit times the four suit, which is 20. Okay. So you can see that at first it seems kind of outrageous. How are we going to figure that out? But when you start actually analyzing it, these things are usually um, pretty straightforward. Sometimes you can misinterpret and that's the bigger risk for these probability questions. And some of the questions get really, really complicated. Flipping coins and rolling dice, flipping coins and drawing cards. It gets on and on and on. And again, there are whole classes you can take on just probability, which um, the, yeah, probability. Um, there's also a probability in data management, I think grade 12 class, where they combine both of them. And again, there's a lot more to this topic. And of course, knowledge of it's going to be a skill that employers will be looking for. All right, let's work out the probability. The probability of, I don't even know what to call that. I'm just going to put an exclamation mark. Um, and there's still 52 cards, right? So they didn't do something strange like, only the red cards or something like that. Okay. And so 20 out of 52, it's a little under half, isn't it? I think I got by 52. Yeah, it's a lot under half. So that's going to be 0.38, approximately 38%. Might be, yeah, it's 38.4. So that was the probability. Now let's go back and take a look at some of the other ones. So we've done this one. We've done this one. Now you see here, question 3. We're talking about one die, and this is why I talked about that at the beginning. It's not as pedantic. It's not as kind of unimportant as it may seem, because a lot of students get all the way through elementary school and never hear that one of them is called a die and two of them are called dice. But when you start reading mathematics in high school and in college, then they're going to use the actual terminology. So one die, so now we know what it is, right? 1 to 6. What is the probability of rolling either a 2 or a 5? All right, can we work that one out? See, if we think about the well, let's make a page here. This is a sample support question 3, still page 22. And what we want here is the probability of a 2 or a 5. Well, if I roll one die, 2, 3, 4, 5, 6. Those are the possible outcomes. Those are the only possible outcomes. Now, how many of those possible outcomes? All right, so 6 is my my sample space, 6. Now, how many of those are meet the outcome that we're looking for? Well, there's a 2 and there's a 5. That's it. So there's only 2 of them that meet our criteria. 1/3 or 33%, right? 33.3%, something like that. Okay. So it seemed like it might be a little bit tricky, but not so bad. Now the question 4 is interesting just because you're using some kind of Vegas terminology or so again, gambling terminology, but using 2 dice, okay, we know what that is. What's the probability of rolling snake eyes? Snake eyes, yeah, that's a slang for double ones, which just means that you got a 1 there, and then the other one, the other die from the pair, also has a 1. Okay, now snake eyes. I don't know what like double numbers are a big deal in gambling and in dice games. If you ever play backgammon, the doubles they really rule the game. It's an exciting game because when doubles happen, especially in near the end of the game, it can just change everything. So yeah. So using 2 dice was the probability of rolling snake eyes. Okay. How are we gonna work this one out? Let's support question 3. Support question 2. No, 4. Support question 4. Page 22. Okay, so we need the probability of snake eyes. 1 is what we're looking for. Okay. Well, how many possible outcomes are there in this kind of thing, right? Can get kind of tricky. If I roll a dice, I could get a 1 and a 1, correct? I can get a 1 and a 2, a 1 and a 3, a 1 and a 4, 1 and a 5. These are two different dice, right? But you're rolling them at the same time. This is dice number 1. This is dice number 2. Okay. All right. So I can get 1, 5, and I can get 1, 6, and then I can get 2, 1, right? 2, 2, and so on. Oh boy. Can we work this out without having to enumerate, having to list all of these? Okay. Well, let's just move these up here. So 2, 1, 2, 2, 2, 3, 2, 4. There's a pattern to this, isn't there? Now, if you actually take a probability class and they'll also talk about permutations and things like that. So they'll actually give you some tools to work this out without having to go through sort of this type of exercise. You'll actually be able to calculate in advance. Whoops, what did I just do? All right, sorry about that. So 3, 3, 3, 4, 3, 5. Maybe you'll get the idea that there's 1, 2, 3, 4, 5, 6 rows, and then we're going to have a 4, a 5, and a 6, right? This will be 4, 1, 5, 1, 6, 1, right? And then these will all be filled in. So how many are we going to have? We're going to have our total is going to be six rows in each row, and then there's 6 columns altogether. So our total is 36 36 items in our sample space, right? If we throw 2 dice at the same time, there are 36 possible outcomes. Okay, so that's what it's going to be, 36. Okay, and that's really, once you've seen this once, then you're probably not going to have to go through that exercise again. You'll just know that 2 dice gives you 36 possible outcomes. And you could work it out with 3 dice too. It gets even more complicated. So now what about the probability of getting a 1 and a 1? How many different ways can we get a 1 and a 1 in this? Okay, well, the only row that has double ones is here, and the only column that has double ones is the first column. Okay, so it means that out of the 36 possible outcomes, there's only one chance to get a 1 and a 1. Okay, there's only one outcome that's 1 and 1. Okay, which, and you see the very low probability there, and that is exactly why doubles, right? The probability of getting a 5 and a 5 is the same. The probability of getting a 2 and a 2 is the same as well. Okay, these are all very low probability events, and that's why doubles in gambling are such a kind of a cool thing. You know, they're used quite a bit to kind of make the game more exciting because they're rare, and when they come up, you know, they're used to really change things up. All right, so what's 1 divided by 30? 1 divided by 36, it's 0.027, we'll call it 78, and then we'll turn that into a probability. It's we'll call it 2.8%, really low probability. Okay. And so that's going to be probability of throwing 2 of the same number. Okay. So, yeah. Now, that's a little different than throwing different numbers, right? Because, for example, we can throw a 2 and a 3, and we can throw a 3 and a 2, which are really, you know, it's the same number. I don't know, you know, if we don't distinguish between the dice, there's actually 2 possibilities of getting a 3 and a 2 out of the 36. So it's a higher probability. All right. Now, let's take a look at. As a matter of fact, I think that this next example talks about what I was just kind of addressing. What is the probability of rolling a 2 on one die 3 consecutive times? So now instead of snake eyes throwing 3 dice, what we're asking is for each time. So we're gonna the first time 4, 5, 6. We're looking for the 2. So our probability is 1 out of 6, right? But then the second time we have the same thing and the probability is 1 out of 6. Right? And then the third time the probability is 1 out of 6. Okay. Well, the way it works is that the probabilities of over a consecutive trial actually multiply. Okay. So the way they've chosen to show it here is it's 1 over 6 to the power 3. Okay. Now, if you, it's been a while since you've done some of these powers. We did a few powers earlier, but just remember that it's going to be the way we do this. It's going to be 1 to the power 3, 6 to the power 3, which equals 1 over 6 to the power 3. That's the up arrow or the y or the x on your calculator. It's a very, very small percent. 0.46%, not 0.46, it's 0.46%. So not even half of a percent probability of rolling 2, 3 times in a row, or any number, right? So you can imagine we could actually ask the same question about rolling a 1 or any other number, and it would be the same probability. Okay. Same thing, if I said, what's the probability of rolling a 1, then a 2, then a 3? You're going to have exactly the same probability, right? The 1 has 1 out of 6, the 2 has 1 out of 6, and the 3 has 1 out of 6. You multiply them together, and that's your probability, okay? Yeah, multiplying things together, independent events, multiplying probabilities together is kind of a fundamental idea in probability. And if you do take that grade 12 course that talks about this, you'll spend a lot of time looking at that. Great. Now, so with that in mind then, if we look at page 23, question 5, remember that the probabilities multiply. So this is support question 5, and that's page 23. So the probability of heads 4 consecutive times. So heads, heads, heads. Okay. So if we flip a coin, this is trial 1, so we can have a head or a tail, right? So our probability is a half. And trial number 2, right? We can have a head or a tail, and the probability, whoa, not 2 heads unless it's a special coin there. So our probability is 1/2, and so on, right? So if we look back on that example we just did, if the probability for each trial is a certain amount, then the probability for, say, 4 in a row is going to be that probability for each one to the power however many trials you had. Okay. So which is kind of cool. So we're going to have it's going to be 1, I could say 1 to the power 4, but 1 to the power 4 is just 1, and 2 to the power 4. And I think what is that going to be? 2 to the power 4 going to be 16. 1 over 16. Okay, or 6.3%, something like that. Not so bad. So now you know how to calculate the probability of any string of heads or tails, right? If I told you it was 5, right? What's the probability of getting 5 heads in a row? Well, you change that to a 5, right? And here's the beauty of this. The probability of a head or a tail is still a half, no matter, right? So if I said, what is the probability of tail, head, head, tail? it doesn't change our scenario. It doesn't change anything really, because the probability of getting a tail on that first trial is still a half. The probability of getting head on the second one is still a half. Probability of getting head on the third one is a half, and the probability of getting a tail on the last one is also a half. So it really doesn't change anything. And that's kind of the neat thing about when we start to look at probabilities, that even though, say, you would say that, well, getting through 4 heads in a row is a very low probability event, it is, just 6.3% of the time. The fact is that getting 4 of anything is a low probability event. So that's where probability, we think of the special cases, say 4 heads or 4 tails, as being somehow unique, but they're actually come up with the same probability, same low probability as everything else. All right, well, let's real quick now just wrap this up. We'll take a look at support question 6. Okay, so what is the probability of drawing an ace from a deck of cards on 2 consecutive draws? The first draw is placed back in the deck, and then the deck is shuffled prior to the second draw. So what they're basically saying is if you have 2 fresh decks of cards, or so when you take that first ace out, you're not reducing the number of aces because you put it back. Okay, so what's it going to be? So this is the probability of an ace and an ace. Interesting, eh? Well, you know what? Let's leave that one for tomorrow's class. So think about that. And when we come back for tomorrow's class, which will also be pre-recorded, we'll pick that up right there. All right. Well, we'll talk to you tomorrow then. Bye now.